Alright, to start off, we're given mass in kilograms. We're given the original height that the block starts off with. We are given a distance where there's a coefficient of friction. That's between point B and point C. My distance is 3.8. We're given a spring constant in kilonewtons per meter, which we need to convert to newtons per meter just by multiplying by 1,000. And then we are given the spring compression, which is x minus 5 centimeters. So that is also going to need to be converted back to meters by dividing by 100. From here, the overall goal is to figure out the coefficient of friction. So if we think about the initial situation, we start off with some gravitational potential at the top of the ramp on the left-hand side. As it's going down in the green section, it's going to encounter friction. And so there's going to be some work done by friction to take away some of that energy. Now, at this point at the bottom, it has converted that gravitational potential into kinetic energy, but we're just looking at the initial state and the final state. All right, now when it gets down to the very bottom, it gets through that green patch, and whatever energy it has left after it's lost some due to friction, that's going to go into compressing the spring. So it still has some kinetic energy, but that kinetic energy, what's remaining, is going to be absorbed by the spring. That's going to go into elastic potential. So this is our big picture. At the beginning, we start off with gravitational potential. There's some work done in the green section, and then at the end, we have spring potential. From here, we're going to expand this and ultimately solve for the coefficient of friction. Not too big of a stretch. This is just mass times gravity times the original height. The work done by friction, that would be the coefficient times mass times gravity, and then that is times the distance between B and C. At the end, that's going to be equal to the spring potential, and the spring potential is 1/2 little k, the spring constant, times x squared. So at this point, we know all of our variables. The only thing we don't know is the coefficient, and that's what we're going to isolate and solve for. Alright, so I skipped the algebra just to simplify things and save some time. If you want, by all means, you can plug in your numbers before we get to this point and manipulate it and solve from you that way. So to save space, I'm just going to plug in my numbers and I'm going to get my answer. And my answer for coefficient of friction is going to come out to, and it gives me 0.2541. The coefficient should be less than 1, so that should give you a big hint on whether you get the answer right or wrong. But this is what my answer comes out to. Alright, for part 2, it says for this value of mu, to what height would the block return at point E, so that's h prime, the final height, should we reverse things? So if we reverse things, then that means let's start off from scratch, and let's say that it starts off with the elastic potential over here on the right hand side. And then when it returns back through that green patch, we're going to have work done by friction. And whatever's left over, that's going to go into gravitational potential. So it's essentially the equation we started off with before, just in reverse. Alright, so our US, we can calculate what we have. and, well, let's just expand it back out again. So this would be, again, 1/2 times k times x squared. Just like before, we're going to have the same work done by friction, so it's still the mu times mass times gravity times the distance between B and C. And that's going to be equal to mgh prime, where h prime is our final height. So this will be much easier for us to move around and to solve for. We would just end up dividing mg, and it'll clean up pretty nice. So let's see what it comes out to this. So I get kx squared over 2. Now when I divide mg, I'm going to go ahead and just distribute it. I'll divide mg to the left. Nothing cancels out in that part. But over here in the green section, we're going to do mu mg times the distance, and we're going to divide that by mg. So the mg's will cancel out, and what I'm left with here is mu times the distance between B and C. That is going to be equal to just h prime. At this point, we can plug in our numbers and get an answer. And again, I'm going to skip this step with my numbers just to save space, but I'll tell you what my answer comes out to, and that's going to be 2.269. Now, remember, since energy is conserved, we understand that your height for h prime here, it has to be smaller than the original height you started off with, because you lost some energy. It can't return to the same height. All right, for part 3, suppose mu is changed after releasing the mass at point A. Mass travels over the rough portion of the track, BC, bounces off the spring, travels a distance of 3.3 meters partway back across the rough portion, and it comes to a stop at F. So under these conditions, what is the value of mu? All right, so now we're merging this all together. Yay. Okay. So we start off with our gravitational potential energy at the top, just like what we did last time. It's going to slide down, and we're going to lose some energy due to work done from section BC. Now, it has a new value for mu now, so we're not going to worry about that just yet. It bounces off the spring. We're going to ignore the spring, because once it bounces off the spring, it's going to give up that energy again, and it's going to return, and it's going to travel the path from C to F. So, in other words, there's going to be more work done from point C to point F. So, it comes to a stop at F, meaning that all the energy that we started with at the beginning is going to get lost on the green section. So it loses a chunk of it on the first pass, and then it loses the rest on the second pass when it's backtracking. So this has to be equal to 0. If we move this around, what that means is the potential energy has to be equal to the sum of the work done in the section. So there's work done from B to C, and there's work done from C to F. All right, now let's just clean that equation up, and we're going to expand it. So mass times gravity times the original height. That's equal to, all right, our first pass. That is the new coefficient, mu, times mass, times gravity, times the distance from B to C, plus mu times mass times gravity times the distance from C to F. And you'll notice that each of these pieces, they all have M and they all have G. So what I'm going to go ahead and do, mg cancels out, mg cancels out, mg cancels out. We can only cancel it out because mg is in each piece. So let's rewrite that a little bit cleaner. The original height is equal to the coefficient times the distance from B to C plus the coefficient times the distance from C to F. Now we have a commonality in the right side, so we can factor out mu. So that gives us h0 equals just mu, and then in parentheses, this is dBc BC plus dCF. In other words, that's the total distance that is going to be sliding and losing energy. And at this point, this should start looking very familiar because we kind of simplified and derived this on the last question. So our coefficient of friction mu is going to be a ratio between the height that the block starts divided by the total distance that it ends up sliding. It just happens that it slides two separate distances, but it's still over the distance that the block has to slide to come to a stop. So I'm going to go ahead and plug in my numbers. Now, I understand that the coefficient I solved in part 1, that coefficient was too small to stop the block. This coefficient is able to stop the block, and so as such, I should have a larger coefficient, but still less than 1. 0.5915. And that will be my final answer for part 3.